Hello everyone, welcome to today's webinar on Footbridge Vibrations to Eurocodes. Today we'll be discussing about different aspects of vibration analysis of footbridges. We'll talk about dynamic analysis and how to check serviceability criteria for human-induced vibrations. Okay, we'll be covering the following topics today, starting with modeling of footbridges. We'll look at two different types of footbridges, one a simply supported bridge and the other a continuous bridge. Both will be having a structural steel as their material. And then we'll move on to basis of footbridge design and dynamic analysis, and then finally look at some of the vibration checks that we usually follow as per Eurocode. Okay, to start with, let's have a look at how the footbridges should be modeled so that we can end up with the correct model for vibration analysis. Normally, we would do a line model for footbridge checks in terms of vibrations. We make sure stiffness properties are correct because these will determine the natural frequency of vibration of the footbridge. For composite steel type of footbridges, we use gross concrete properties, that is uncracked properties. We should include the dead loads and all superimposed dead loads as mass information for the vibration analysis. And for lightweight footbridges, should make sure that component of the live load is also considered as a mass. Another important thing to be ensured that model has been defined with this particular thing is boundary condition. So whenever we have soil springs or we want to model soil structure interaction for pile foundations, it should be very accurate. So I'll just quickly run through some of the models that we are going to look today. Right. So here is the first model. It's a simply supported bridge, a stressed ribbon kind of structure with a central spine of structural steel and uh, an arrangement of plan bracings. Then just to look at how it has been modeled, it's just that the central spine has been modeled with plate elements to make sure that stiffness of the spine is assumed correctly. The rest of the the rest of the elements are line elements of various types. Like we have the bracings modeled as bracings are modeled as moment releases, and the other elements are all beam elements. So there are some releases applied here. So you can see them. These circles are the releases, and the mass of the structure, the entire self weight of the structure has been converted into mass using the lumped mass feature. And apart from the self weight, the dead loads, the superimposed dead loads like the deck panel loads. Deck panel loads are applied as a UDL throughout the bridge, and they have been converted into loads to masses. As you can see here, pedestrian loads are also converted into mass, so 10% of the pedestrian load has been considered in this scenario as a mass on the entire structure. Okay, so this is one example of a footbridge which is simply supported. Just to show you the support conditions. So here we have 4 bearings, pinned and roller type of bearings. Now let's look at the second type, which is a continuous bridge. Okay, the second example is of a continuous curved type of bridge. It's a 3-span continuous composite steel structure which is supported on single piers, and the piers in are supported on monopiles. So here we have the section of typical section of the deck defined. So it's a composite deck slab with a steel box section. Again, we have used gross section properties of the deck, so we have not assumed any cracking in the deck. So again, the entire self-weight is converted into lumped mass, and a portion of the pedestrian load is also converted into masses shown here. Okay, and you will see soil springs defined for soil structure interaction. So elastic links have been used, they have been defined with certain properties. Okay, going back to the presentation. Okay, now we'll have a look at the basis of footbridge design. So for any type of footbridge design, apart from the normal ULS checks which are static in nature, ULS and SLS checks, apart from that we have mostly focused in this presentation on vibration design. So whether the footbridge is sufficient to withstand the vibrations, as in from the comfort zone of the pedestrians. So our ultimate goal is to basically check the acceleration of the bridge when the pedestrians are walking or jogging on it, or when there is a crowd condition. So in order to calculate that peak acceleration, we need to carry out a dynamic analysis. So the first step in this design is to carry out a free vibration analysis just to determine the natural frequency. So any natural frequency analysis will depend on the stiffness. So as seen on the right hand side, it's a spring analogy. There is a spring stiffness and then there is a mass. So based on these two properties, the body can vibrate in a free manner in certain frequency. So after determining that frequency, we compare it with the code limits. If the frequencies are less than certain limits for vertical or lateral vibrations, then the code suggests us to do a more complicated analysis, that is a pedestrian time forcing function analysis, where we actually model the moving pedestrian and the load applied by the pedestrian varying with time. So it is checked for different velocities, like if it's a walking or jogging case, or if it's a steady state like crowded condition. And then after that we end up with an acceleration versus time response, which is then checked against the code limit for acceleration, and that's how we can say that the bridge is safe for or it pertains to the serviceability criteria for comfort criteria of pedestrians. Okay, so free vibration analysis or eigenvalue analysis, as mentioned before, it depends on the stiffness and mass of the structure. So there may be different modes of vibrations. We have to identify the correct vibration mode which applies for the particular check, lateral or torsional or maybe vertical vibration. So let's see how in the software we can carry out such kind of analysis. So for eigenvalue analysis, it is important that the stiffness, boundary condition and the mass of the structure has been defined correctly. So in the previous few slides we saw how the model is set up initially, so that we have the correct stiffness and mass in it. The next step is to just specify how many modes or how many frequencies we want to calculate, and that is done through the eigenvalue analysis control. So we set up the number of frequencies for the check, and then after that we check up the vibration mode shifts. So there are different modes analyzed. So this is the first mode of vibration. So from visual inspection, it seems it's the lateral mode of vibration. To make sure, you can always check the animated view to make the structure animate basically. So checking mode number 2, which is again a lateral mode of vibration. Okay, mode number 3, this looks like a vertical mode of vibration with alternate crests and troughs formed. You can also check the modal mass participation factor, that is what percentage of mass has participated in x, y and z directions. So this is how it is displayed. It shows up the individual frequencies of every mode and the mass participation. So how do I cross check whether my first mode is the lateral mode? We can always have a check on the mass participating in which direction. So here we can see mode number 1, maximum mass participation happens in y direction or the lateral direction, whereas z has zero mass participation. Vertically there is no mass participation. Similarly, mode 3 has more of vertical mass participation, although the mass participation percentage is low, but compared to other directions, we can see this is more participating vertical direction. And of course, visual interpretation is also there to identify that which mode is vertical or lateral. For a simply supported structure, it becomes more simpler. So if I open the previous structure which I was showing for simply supported case, okay, so for this type of structure, that's the first mode is the vibration mode here. Second mode is the lateral mode of vibration, so as you can see here, and we can check the mode frequencies and the mass participation factor. So 67% mass participating in the first mode itself in vertical direction. Similarly, 67% mass participating in y direction in the second mode. So clearly indicates that mode 1 is vertical and mode 2 is lateral. So once we have identified that, the next step is to check whether we need a complicated analysis to say that the bridge is successful in serviceability check for comfort criteria of pedestrians. So Eurocode says that if the vertical vibration frequency is within 5 Hz, 5 cycles per second, then we need to do a detailed vertical dynamic analysis, a vertical vibration analysis. And if it is less than 1.5 cycles per second for horizontal or torsional vibrations, then a lateral frequency check is required. Okay, now how do we do such kind of checks? First of all, we set up a separate time history load case. The time history analysis is that we do in this kind of scenario is a linear modal superposition analysis, wherein we take up the summation effects of different modes of vibrations, add them up in a linear manner, and apply a damping coefficient to it to all the modes. So usually for in Eurocode it is given which is in Eurocode 1, it's clearly given for what type of materials, what is the damping ratio that should be used. So that damping ratio or logarithmic damping, which we say is, let's say, 4% for composite steel bridges, which is then modified to structural damping ratio using this formula and applied it in the software. Okay, so just to quickly go through, so let's take this one as an example. So you go to dynamic loads, and here we have an option of load cases. So let's say a walking load case. We define the analysis type as linear, method as modal. Ending time is 40 seconds. This will be determined by the length of the bridge divided by the speed of the pedestrian. So it should not be less than that value, whatever we get from this exercise. And the time increment, that is for how many increments you want the output. So basically how many time steps you need. And after that it shows a load case is defined. Once the load case is defined, the next step is to define a forcing function. So Eurocode has stated some ways of calculating the load functions, which we will cover in the next few slides. different types of load models are there. So they are generally in a sinusoidal form. So this kind of curve is there for one time period. We make sure that the forcing function has the same frequency as that of the critical mode. So for example, if we are checking for vertical vibration and we are checking for vertical walking loads, so the vertical walking loads should be having the same frequency as the first or the most critical mode of vertical vibration. So in this case, in this particular example, whatever was the frequency of the first mode, which is the vertical mode, that will be used as the same as the frequency of the loading. Okay, so that will produce a resonance effect. Now once we have this forcing function defined, it's all a matter of selecting the points or the nodes on the structure where the loads will be applied. So if I just remove these things from the view, so there's something called dynamic nodal loads. So excuse me. So we have a walking load case and function name as walking. We select the direction as Z direction, which is the vertical direction. This is where we enter the arrival time. So if I select node number 1 and put in some scale factor, say 1 or whatever, or -1 if I put it in the downward direction, and click apply. So that's my first point where the pedestrian will put his foot. Then the next step is, after one time period, let's say I put in the arrival time as some time period, and the next node should be loaded. So I select the next node and click apply. How do I know that which node the pedestrian will land? Well, that is defined by the velocity of the pedestrian multiplied by the arrival time. So from this node to this node, whatever is the distance, that should match the velocity multiplied by the time period of the pedestrian. So that to make sure that exactly at the correct points I'm applying the loads, and at the correct time intervals too. Okay, so this is how we do it for moving pedestrians. And for crowded pedestrians, we just apply it at all the nodes and at the same time only. So as if all the pedestrians are jumping on the bridge at the same time. So this is how it will look like. I'll just display the. So that's how it looks like after applying the dynamic nodal loads at equally spaced nodes. So once we have completed that dynamic nodes, we'll run the analysis and we get this kind of acceleration versus time plot. Now there may be a scenario where we may have to change the orientation of these dynamic point loads that we have applied. So in the case of simply supported structures, it is a straightforward measure. The mode shape will be having one single pattern. So it will be either there will be no anti-node in between. Whereas in the case of a continuous structure, there can be an alternate pattern, that is we may have a crest at the end span and a trough at the mid span in a three span bridge. So let's see how we model these point loads in such scenarios. Okay, if you remember, the vibration mode shape of a vertical mode was an alternate type of mode shape for each span. So the end spans had a sagging kind of pattern, and the mid span had a hogging kind of pattern. And the crowd loading that we applied in such scenarios is this way, so that we get the maximum acceleration out of the structure. So whichever direction the mode is vibrating, that particular direction I apply the loads. So it should be kind of this alternate kind of setting. Okay, so now let's see what are the time functions that are used and how they're calculated. So Eurocode has defined few load models for walking and jogging pedestrians, and also crowd condition. So for example, it will there are few parameters on which this load function will depend. This is the equation, as I mentioned before, is a sine function. So the basic force is defined from table 8 in the National Annex of UK. This is the pedestrian speed for walking and jogging. Then for different scenarios of the bridge, so for example, depending on the location of the bridge, whether it is a rural or suburban or urban location, the group size of walking or jogging will be defined, or the crowd density will be defined. And based on the frequency of the structure, there is one K factor which is calculated from this graph, and then there is a reduction factor gamma which is calculated from this particular graph. And based on these two values, we can calculate an amplitude for this sine function, which is then applied in the model as a time forcing function. Now, where are these time forcing functions applied? They are applied as dynamic nodal loads at the nodes on the structure, which are spaced at the intervals of speed multiplied by time, which I just now discussed in the previous slide. That is how you define the node spacing. Okay, so before modeling, it is good to have a check of what kind of node spacing you should end up with. It doesn't have to be very accurate, but it is good always to, so that we get the maximum possible acceleration out of the model. Then the next step is for crowded condition, for crowd loading, crowd vertical loading. In this scenario, the load that is calculated is not a point load, but rather it is a distributed load, W. And that depends on, again, the similar factors, K factor, which is calculated from this graph. Then there's a reduction factor, and then there is one more factor, which is lambda. This lambda is something which will depend on the mode shape itself. So what we do here is we first calculate the effective span that is participating in the vibration frequency. So let's say in the first mode of vertical vibration for a continuous structure. For a simply supported structure, it is fine. It is straightforward. It's just effective span is equal to the net span. But for the case of a continuous structure, we find the areas for each mode shape. That is like, for example, in this particular case, we have a mode shape that looks similar to this. Let's just display it again. Okay, so mode number 3 is the vertical mode. Yep, so it looks like this. So we calculate the area of the mode shape for each span. To do that, we need to know what is the mode shape value. So what is the displacement value, and that we can calculate from the legend shown here, or we can take it from this table. So we have got some a separate table for eigenvector. So eigenvector can be displayed once you select which mode you want. So mode number 3, let's say. This is the eigenvector for mode number 3. And these are the actual values of Z, or the displacement in the Z that is happening in the mode shape. These are normalized values. So that can be used to calculate this effective span, and then lambda is calculated, and that's how we end up with the per meter square time forcing function applied for crowd loading. And then once we get the per meter square value, we then multiply it with the node spacing that we have assumed in the structure, and we get the that's how we end up with the point load applied at different nodes, even for crowd loading. So how is the crowd loading applied? It's not applied as a single sine function with a single time period. It is applied as a continuously oscillating function. So something like this fashion, this type of a sine function, which is periodic in nature, is considered over here. Okay, the next category is lateral vibration checks. So for lateral crowd loading, it's a bit unclear in Eurocode on how to do this type of check. If the frequency is less than 1.5 cycles per second, then we need to do a complex check for lateral vibrations too. So first step is to make sure that whether the structure is stable by doing a quick mass damping parameter check. So we calculate mass damping parameter as the ratio of mass per unit length of the bridge multiplied by damping ratio divided by mass per unit length of pedestrians Okay, so once we obtain this D value, we compare it with this graph. If it falls within this graph, A being the frequency of the lateral mode and B is the pedestrian damping parameter that we calculated from above. If it falls in this category, C, it's unstable, and if it's D, then stable. If it is unstable, in that case we have to carry out a separate lateral vibration check for the model. Now the method is not clearly given in the national annex, but it is given in some other publications, technical material, which is the JRC publication reference 1. This particular equation is used for calculating the lateral loading. Okay, and it depends on few similar factors. So there's a table which shows what kind of amplitude should be considered for lateral loading, and then there's a reduction factor to take into account the unsynchronized response of pedestrians. Okay, so there's a psi factor over here, and then there is equivalent number of pedestrians is also calculated, n dash. Okay, so that's how the lateral crowd loading is applied. Now let's see in the model how it is applied. So in the analysis model, first of all, because it's a curved bridge, so lateral direction application force will not be easy to do if we use just the global coordinate system. So to make sure we have the correct orientation of the loads applied, we use the element beam loads feature to first apply static loads. So that's how we have assumed that element beam loads are applied in the local direction of each element as point loads, and these loads all have a unit value. Okay, so they are all 1 Newton loads. Okay, then what we do is we define a unitless lateral loading function, so, which looks something like this. So we apply a unitless normal as mentioned here, not force, not moment, but a unitless time forcing function. So the next step is then to just multiply that unit load which we applied as static loads with this time varying function. So that option is over here, time varying static loads, where we select the time history load case and the static load and then multiply it with the corresponding function, and then this is automatically applied to the structure at a single time. Okay, so that's how we apply lateral crowd loading. The next step is the actual checks that we do, the vertical checks and the lateral checks. So for the vertical vibration checks, the acceleration versus time plot is first generated, and that is checked against the limit acceleration defined in the code. This acceleration is calculated using these three or four factors over here, like site usage factor or route redundancy factor, structure height factor k1, k2, k3, k4, and whatever limit we get, if it is less than this limit, whatever acceleration we're getting, then it is okay, it meets the comfort criteria. If not, then we need to control it using some external methods like vibration controls, which we'll discuss later. So let's see how to do a vertical vibration check once we have got everything set up, the load model set up and everything. So the next step is we first check whichever point can have the maximum acceleration. So out of all these nodes, there are so many point nodes over here. We can't generate acceleration time curve for all the nodes, otherwise it will take a lot of time. So we identify the critical nodes. So from visual inspection itself, if our goal is to check the vertical mode, if we check the first critical mode of vibration for vertical direction, we'll find the mid-span center node is the critical one. Okay, so that gives us one idea. So if I just select this node number 101 for instance. Okay, so that gives us an idea that 101 can give the maximum acceleration. But to double check, we can always go for deformations and check maximum acceleration based on crowd vertical loading. So suppose ground vertical loading. So acceleration and dz. Okay, so it gives maximum acceleration is at node number 99, which is pretty much close to what we had assumed, this particular node. So let's check up what is the maximum acceleration, what is the graph maximum acceleration curve for this particular node. So for we can use the time history graph option to plot it. So first we define a function. So let's say node number 99, we define it as dz99. Acceleration direction is dz, and we have to define the correct load case for which we are checking. So there are different load cases. In continuous type of structures, we can't just put in alternate loadings and say that it is the critical load. We should check for other cases as well, like for example only mid span loaded, or only the side spans loaded, or only let's say two spans loaded. So here, like you can see, there are several such load cases created. So I'm just checking for one of them, which is the all spans loaded with alternate directions based on the mode shape. So I've selected this as the vertical axis graph. Okay, and that's the kind of graph that I get for the maximum acceleration. So maximum acceleration is coming to be around 0.73 meter per second square, and this needs to be checked against the code limit. Okay. Similarly, our next goal is to check also for lateral vibrations. So for lateral vibration checks, the code doesn't really specify, Eurocode doesn't really specify in the National Annex any such code limit for acceleration, but JRC publication gives some values over here. That is, the lateral acceleration should be below 0.1 meter per second square for the acceptance criteria for stability. So to check that, let's see again in the same example. If I go back to vibration mode shape, maybe go to mode number 1. So it seems again there are two things here, one is mode number 1 and mode number 2. So it is basically superposition of these two modes that we will be interested in. So from visual inspection, it seems that again this center node is what is the critical one for lateral vibration check. So we will just simply select one node over here. Let's say node number 99 again, and we'll plot the same graph. So this time it's node number 99. Let's say it's a dx. So this is x direction acceleration, and this is lateral perpendicular direction. Okay, so this is the acceleration value for the lateral vibrations. So it's somewhere about 0.02 meter per second square, which is well within the 0.1 meter per second square limit. So that's how we do a lateral vibration checks. So we have covered the two most important checks that we do for any vibration check, which is vertical and lateral vibration checks. We have seen Eurocode load models. Now what if still it doesn't satisfy these acceleration limits? In that case, we need to go for vibration control. Now vibration control techniques can be, there are different can be different ways of controlling vibrations. The number one is if we modify the mass of the structure. So for as mentioned earlier, for very light footbridges, the pedestrian load tends to act as a mass and can lead to a lower frequency of the structure. So we need to use heavy concrete deck slabs, which can improve the dynamic response of the structure. um, and this is very commonly used in stress ribbon type of structures which have a light deck and a central spine, so we make it heavier by using deck slabs. Then modification frequency, that is actually increasing the frequency itself. This is best done by modifying the structural stiffness. So our goal is to because your frequency is related with the square root of stiffness upon mass. So the way we do it is we replace non-continuous panels by continuous slab maybe, or maybe include handrail as a structural element, or just modify the depth of the steel box girders, or maybe thickness of the lower flange of the box girders. Okay, just playing around with the thickness and the depth. But these may have their own limitations because we may be hindering with the aesthetics of the structure. So there are some alternate ways also to stabilize the structure from a lateral vibration point of view. One of the ways is introducing a cable system. Okay, and again in cable structures, it is seen that an A-shaped pylon or an inclined type of cables make the cable state bridge more stable against lateral vibrations, as opposed to just symmetric or maybe vertical alignment structures. Now, if these two things are not possible or not feasible, we have to then go for damping devices. So how to increase damping? The more damping means more dissipation of energy through damping methods, and the less will be the acceleration. So one of the ways of increasing damping is introducing wire mesh face on the handrails, and the other is introducing external devices like viscous dampers or tune mass dampers as shown here. So this is a viscous damper example. Is tune mass damper, okay, which these devices can play around with the damping of the structure and thus help in dissipation of vibration energy. Okay, so that brings us to the end of the presentation today. I hope it covered most of the issues on vibration analysis of footbridges. If you have any questions or need any free demonstration, please contact the Midas UK support team. Details are shown over here. Thank you. Bye bye.